This is Mr. Martin. These are the video notes for Pre-Calculus Honors. This is Section 8.1. This is the second day of Section 8.1. So the first thing that we're going to talk about is summation notation. And really this is just a notation, a shorthand notation to indicate that we want to add up a bunch of terms in a sequence. And we can do this for a finite sequence, or we can do it for an infinite sequence. So if you notice the notation here, the way I would read this is the sum as I goes from 1 to n of a sub I. And a sub I is normally going to be some function. And what we do is we're going to substitute the values for I into the function, going all the way up to the value of n, and then add those all up. So we would have the value of the function when I is 1 is a sub 1, the value of the function when I is 2 is a sub 2, and the value of the function when I is 3 is a sub 3, and then we would keep substituting in all the way up to the value of n, and then add those up. So let's go ahead and take a look at a couple examples. And although there are ways to do this on your calculator, we're going to look at it doing it by hand first, and then we'll look at the calculator. So for the first one, our function is 4i plus 7, and we want to add up all the terms of the sequence that are generated by using values from 1 to 6. So the sum as I goes from 1 to 6 of 4i plus 7 is going to be 4 times 1 plus 7. That's going to be the first term in the sequence, plus 4 times 2 plus 7, plus 4 times 3 plus 7, plus 4 times 4 plus 7, plus 4 times 5 plus 7. And then our last one, our last value of I, is 4 times 6 plus 7. Okay, so if we simplify each of these quantities, we're going to get 11 plus 15 plus 19 plus 23 plus 27 plus 31 for a total of 126. Okay, so this is the sum of the first 6 numbers in the sequence that's generated by 4i plus 7. Would be 126. Alright, let's take a look at part B. We're going to plug in values of I going from 1 to 4. So we're going to have 2 over 1 factorial plus 2 over 2 factorial plus 2 over 3 factorial. And then our last value of I, 2 over 4 factorial. And if we calculate this all together, you should get 41/12. Okay, so those are just a couple of quick examples. When we're talking about properties of sums, we've got a couple different properties here. And these can be used sometimes to make problems a little bit easier to solve. So if I have the sum as I goes from 1 to n of c times a sub I, so c is a constant, we can really pull the value of c out in front and then just multiply it by the sum that we get after. Okay, and then if I have the sum of a quantity that's addition or subtraction of two expressions, we can separate that into their own sums. And then the last one is kind of interesting because we have the sum as I goes from 1 to n of a constant value. So really what this turns out to be is just that constant value times our value of n. So let's take a look at an example of that. So let's say I have the sum as I goes from 1 to 6 of 10. Okay, so I'm going to use values from 1 to 6. So when I is 1, the value of my function is 10. When I is 2, the value of my function is 10. When I is 3, my value is still 10. and then 10 for when I is 4, 10 for when I is 5, and 10 for when I is 6. So this turns out to just be 10 times 6. That's my value of C. That's my value of N, or 60. All right. So when you sum a sequence of terms a finite or infinite number of times, you're dealing with a series. So a finite series is also known as a partial sum. So some vocabulary that you need to know in case the directions ask you to find a partial sum. So again, for a finite series, we're just going to add up the values of the sequence until we get up to a sub n. And then for an infinite series, we're going to add up all the values up to infinity. So notice this keeps going on. So the interesting thing here is that you can add an infinite number of terms in a sequence and get a finite answer. So we're going to add an infinite number of things and we will get an answer. So again, let's take a look at a couple of examples. So let's start with the sum as I goes from 1 to infinity of 5 over 10n. So when I say find the third partial sum, really what I'm asking you for is the sum of the first 3 terms. So we can write this as S sub 3, the third partial sum, and we're going to be using values of n going from 1 up to 3, third partial sum, so we'll have 3 terms. So we're going to have 5 over 10 to the first plus 5 over 10 to the second plus 5 over 10 to the third. So that's going to be 0.5 plus 0.05 plus 0.005, or the third partial sum is going to be 0.555. Alright, so let's take a look at the infinite sum. So we can see a pattern that's evolving after the third sum is basically we're going to be adding another 5 to the end of this because our numbers are decreasing by a factor of 10. So the sum of this series then would be 0.555 repeating. And if you remember that this is 5/9, that's perfect. It's going to be 5/9. Or if you remember, we can convert this to a fraction if we do a little bit of algebra. If we let x equal 0.555 repeating, and then if we subtract from this 10x, so 10x is going to be 5.555 repeating. So I would get negative 9x over here, and then 0.555 repeating minus 5.555 repeating is just going to be negative 5. And then if I divide by negative 9, I get x is 5/9. So just a little review of how to change that repeating decimal into a fraction. So here's a case where we're adding up an infinite number of numbers and it turns out to be 5/9. So the key to this is that the numbers in the sequence are actually decreasing. So we could say that the sum either converges or it diverges. If it converges, then we can get a sum. If it diverges, then we will not get a sum. And we'll talk more about that as well. So go ahead and pause the video, and you can try this example, and we will discuss that in class. So see what you can come up with, and then when you come back to class, we'll take a look at those. And again, as usual, if you have any questions, make sure that you write those down and ask me when you see me in class. And again, make sure that you have these done so we can discuss them when you come to class. All right, we'll see you next time.